Hello, welcome to this 9-minute supplement on escape velocity for the Gravitation and Black Holes course. The lecture script for all the supplemental videos is available at a link given in the description of this video. Newton identified that the gravitational force between two masses that are point sources or spherically symmetrical mass distributions is always mutual, each to the other, attractive, directed along the line of their centers, directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Larger distance produces smaller force. With the masses in kilograms and the distance in meters, the force is in newtons, kilogram meters per second squared. We can think of Newton's gravitational constant g as merely the conversion to a given unit of force. We will consider the case of a small body of mass lowercase m attracted to a large body of mass capital M. Gravitational attraction is a conservative force, meaning that we can find an expression for the energy of the system that depends only on the positions of the bodies, or in this case, the separation between their centers, lowercase r. The gravitational potential energy U of r equals minus g times the product of the masses divided by the center distance r. At infinite separation, the gravitational potential energy is 0. At finite separation, the gravitational potential energy is negative because the force is attractive. The negative potential energy is a binding energy. For a small object at rest on the surface of the larger object with radius capital R, the gravitational potential energy is this formula. Here is a graph of that formula. Total mechanical energy is the sum of gravitational potential energy and the kinetic energy. At rest on the surface, here, the total mechanical energy is negative and the small object is gravitationally bound to the large object. If we can give the small object, for example a rocket, enough kinetic energy, the total mechanical energy can be 0 or positive, and the small object is no longer gravitationally bound to the large object and can escape to infinite distance, as shown by the red arrows. We can add kinetic energy until the total gets above the 0 mark, and then we can escape to infinity. From this, we can calculate that the escape velocity from the surface, which is independent of the small mass. This is equating the gravitational potential energy at the surface with the kinetic energy. The escape velocity from Earth's surface is 11.2 kilometers per second, about 7 miles per second, or 25,000 miles per hour, or 33 times the speed of sound. This is much faster than commercial jets or military jets go and they do not escape the Earth. This is 37 millionths of the speed of light. So we don't have to worry about special relativity here. At this speed, a rocket would have to be given 63 megajoules of kinetic energy per kilogram of mass near Earth's surface. This escape velocity will allow a rocket to escape to infinity from Earth's gravity, but not from the Sun, as the Earth is in orbit around the massive Sun. The escape velocity from the Sun is higher than the escape velocity from Earth. Now, we ask an odd question. Could this escape velocity ever equal the speed of light? And if it could, what would that mean? Well, we could just set it to the speed of light and find out what conditions that would mean. Ignoring the fact that Newtonian mechanics is non-relativistic, the large body's radius would have to be this, 2gm over c squared. If you plug that into here, you would get an escape velocity of the speed of light. This is exactly the Schwarzchild radius of a non-rotating spherically symmetrical mass distribution, as we learned from the main course. It's amazing that we can get this number from Newtonian mechanics, albeit bogus, since Newtonian mechanics does not apply at speeds close to the speed of light. Newton thought that light consisted of material particles to explain why a beam of light can be so straight. Some other scientists in Newton's time thought that light was a wave to explain diffraction. However, for 2 centuries after Newton, British scientists generally accepted that light consisted of material particles emitted at the known speed of light, in which case they should obey mechanics and gravitational attraction. In 1783, English scientist John Michell proposed dark stars, from which light cannot fully escape. He assumed an average density equal to the Sun's, in which case his dark stars would correspond to supermassive black holes as we now know them. However, the classical picture of these stars is not the correct picture of black holes. Light emitted radially outward from a dark star's surface would lose kinetic energy and speed as it moved outward from the star's surface, consistent with the gravitational potential energy. The light particle's speed would fall to 0 at some far distance from the dark star, and then fall back onto the dark star. We now know, according to general relativity, that light emitted at or below the event horizon will never escape the event horizon. It does not escape and fall back. And we know that light particles, photons, have 0 rest mass, so they're not subject to Newtonian gravitation, but they are subject to Einstein's curvature of spacetime.